So today, our focus is going to be the class Amphibian. So each day we have a theme. We work with a different group of animals. The first day today, we were going to work with amphibians. And then as we go through the week, we'll eventually get to the copperhead and cobra tomorrow with reptiles. On Wednesday, we'll study birds. On Thursday, we'll do mammals. And then on Friday, we end with the most important, the most exciting, and what you guys really appreciate. I know why you're really here, the arthropods. And if, maybe in years, if we advance, we'll finally get to the group that you truly are most passionate about. So this year and this week, we're focusing on animals, which I know for kids, that is their least favorite group of living things. I know your favorite group is Monera, right? Blue-green algae? That's why you came, isn't it, Corbin? He's like, darn it, we're not doing blue-green algae. And then, of course, Protista. You guys love the protists, right? Second favorite. Then usually fungi is your third favorite. Plants, your fourth. I know, animals are way down the list. You guys don't like animals, but this week we're going to make you suffer. We're going to just concentrate on animals, and then we'll bring in plants and fungi and other things as we're outside and we find the different things. So at this moment, you can open your notebooks, start writing down the notes. I'll give you a few minutes, and then we'll start discussing what are in these notes. The muscle memory. It's always good to write out notes. Between the muscle of your hand writing them, and your brain thinking about writing them, and then when we talk about them, it'll bring all that information into your head. All right, so today, what group of animals are we studying? Class Amphibia. We like to do our Greek and Latin, help you out since you go through school, and of course you're all going to become biologists. So, we'll start with some simple Greek. Amphi means both or double, plus bios means life, both or double life. And that is because they are quasi-terrestrial. So amphibians came and evolved from fish. And as that, they are basically tied to the water during parts of their life, if not really throughout their life. And so while they became the first of the terrestrial vertebrates, they never really completely left water to live on land. And that's because they lack a protective skin covering. They have jelly-like eggs that need to be laid in or very near water or underneath very moist logs. And like fish, they're ectothermic. So whatever the temperature of the air is outside, thermic heat. Whatever the temperature of the air is the temperature of them. Whatever the temperature of the water is their body temperature. And so they are very limited, but they are the first step of a line of fish, in this particular case, the lobe-fin fishes, that led to tetrapods, four-legged creatures, and amphibians would be the first. This all started like 400 million years ago. Quite a long time ago. And in order to make that step, like in all of evolution, there usually is an environmental pressure. And in the Devonian period, which is when this all began, 400 million years ago, really there's a couple pressures. One was the going through wet to dry periods. And this particularly affected freshwater fish. Now, in the oceans, it's different. The oceans are huge. The oceans keep water. In freshwater systems, they can dry out. They become stagnant. They can become very difficult in order to obtain oxygen. And that is what was happening starting 400 million years ago. They're going through serious periods. Now, when I'm talking, you're talking thousands of years. You're not talking days or weeks or like, oh, this spring's been a drought. I'm talking a long period of time. And why having stagnant water is a problem, everybody take a breath. Really easy for us to get oxygen. there's 20 times more oxygen in the air than there is in water, which means that when you are a fish with your gills, you are working 20 times harder to get oxygen than we are by just simply breathing in. And for fish, they have a system in which they have gills. And if you can see the gills, they kind of stack up on each other, loaded with capillaries, tons of little veins and blood for blood flow. And as they wave those through the water, they're able to pull out that little bit of oxygen that's in it, which works well because water has greater density than air. So Corbin, we're going to take you and we're going to put you at the height of the ceiling and we're going to drop you into a pool of water, which I'm going to magically make appear. If we do that, are you going to get hurt? No. You're just going to drop down and then you're going to float up because it's more dense. So the gills, being feathery, can work really well in that medium. Now, Corbin, we're going to put you back up on the ceiling, taking away the water, and we're going to drop you. What's going to happen? You're going to go splat. Thus, the same with the fish's gills. As soon as you pull a fish out of water, what happens to the gills? They go splat, and they can no longer wave. And what's the fish start to do? It starts to struggle right away as it can't not get the oxygen. So gill systems work really well in water, but as you transition to land, not so well. The other thing that the amphibians had to deal with is in water, the temperature stays rather constant. A lot of amphibians like green frogs and bullfrogs take advantage of that. They hide under the ice and they get down towards the bottom, and that's how they spend their winter. And they just take whatever little teeny oxygen they need through their skin, and they remain under the water the whole time. Once you start attempting living on land, you have to deal with crazy temperature extremes, from super hot to super cold, and it can happen on a daily, weekly basis. You saw that in the spring. We had some days that were actually pretty chilly, and then all of a sudden you'd be back up into 75, 85 degree temperatures. Advantages on land, there's a variety of land habitats. You can think about a freshwater lake. There's only so many different spots within that lake that are dramatically different from each other, so there's less variety. And then of course there's many more opportunities for breeding on land, which we kind of get into when we get to the reptiles tomorrow, and really the first truly terrestrial vertebrates that live on land. With that being said, we're going back to that environmental push. So when it's drying out, the gills don't work. You can see this with lungfishes. Still to this day, they will come to the surface barely, and they'll take in like air. And what the first most likely did, and what you can still see with some just non-lungfishes, is the gulping of air and then diving down. And the pressure of the water pressure on the bottom of their jaw pushes the air into their esophagus. And over thousands and thousands of years, when you put that pressure into a tiny little esophagus, eventually it makes the esophagus wall get slightly bigger. And the ones that had a bigger pocket and had more blood flow eventually reproduced more, had more young that were passed on, and the ones of those young that had the bigger pocket reproduced more and passed on the trait even further. And as you go through just hundreds of thousands of years, you get primitive lungs. These become the lungs that you see in the amphibians. And you can see here, from what's more primitive, as you really move into the first tetrapods, that sac gets ever bigger, ever more capillaries, ever more connection. And also, not going to get into aortic arches, but the 7th aortic arch gets usurped, and the blood flow just goes to the lung, back to the heart, where it's then pumped through the other arches to the body. Pulmonary arterial system. All started in the amphibians, which then allowed that lung development and allowed what you see frogs to actually breathe and live on land. Ironically, as you look down, we're going to get into the classification. You go kingdom Animalia, that's the animals. Phylum Chordata. This is the only day we're going to cover this, but we might as well, because you're a chordate. That's a notochord. So when you were a teeny little fetus inside your mom, you had a notochord. It's one of the first things that formed. It's cartilaginous, and it basically runs down all chordates' bodies. That's a very primitive chordate. And it is both support and it protects that central nerve cord where everything radiates from. And soon in the chordate evolution, you get to the subphylum Vertebrata. What's a vertebrate? What do they have, Corbin? Vertebrata. Kate.
Spines?
Yeah, what else is another word we call it? Backbones. So the chordates have a backbone that actually protects it. And so your notochord that started with you as a little infant, that actually gets put into your spinal column, and it becomes what hurts us old men when you have disc problems. You have little cushions in between all of your bones going down your backbone. And as you get older, some people's degrade. But that is and has its roots from the notochord. So we're just concentrating on the vertebrates, in this case class Amphibia, which we already talked about, meaning double life. One of the older, more primitive of the amphibians we still see on Earth today are order Chordata. That's Latin chordates, having a tail. And that is your salamanders. Key. Internal fertilization. They usually lay sperm packs down in the water, and when they do that, they tempt the female in different ways. Here are newts. So this is in a lab, not quite natural, but they do the dances and they grab hold, and they'll actually literally use his back legs to hold onto her head and leads her down to the bottom. And when she gives the proper nudge, he'll drop his sperm packet, and then he'll drag her over it, and she picks it up in her cloaca, which is the one hole in which both waste and reproduction occurs. And then she'll fertilize her little jelly-like eggs and lay them singly throughout the pool. Some salamanders, like the spotted salamander, which is one of the ones that I was hoping to show you today, but I cannot because it's been so dry this spring, the pool dried out, and so I was unable to get them. But spotted salamanders are huge. We do a spotted salamander program in February to March. It's our biggest salamander. And they lay large egg masses in ephemeral pools, pools that will dry out. That's important because they don't hold fish. Fish would be predators to those large egg masses. Unfortunately, in a year like this year, the pool didn't last long enough, and the little salamanders didn't have enough time to grow and get out of it. Unlike frogs, salamanders go from an egg to a little nymph that has feathery gills that looks like a miniature adult to then the adult salamander. Then we get to order Anura, and without or a tail, frogs and toads. That's your famous, most widespread look at the most incredible metamorphosis from going from this egg to this tadpole. It looks very fish-like, that actually has internal gills to breathe, to then developing into the polywog with the legs coming out. First leg actually comes out of the port of where the gill works and takes in water, and you know at that point that it has lungs, and it has to come to the surface to breathe, and then eventually it turns into the frogs and toads. But they have external fertilization. So to kind of end the story of their evolution, you take an animal that 400 million years ago, due to dryness, stagnancy, lack of oxygen, then the age of the amphibians took 100 million years to get to the Carboniferous period. Literally, the light that you see above us, the fan moving, the fact that we have air conditioning, all comes from this period of time. The coal that was basically compressed, boggy plants in a very warm, boggy condition was the age of the amphibians. And the amphibians, instead of continuing to push onto land, they actually became more fish-like. Frogs had webbed feet, external fertilization lake of fish, and what environmental pressure pushed them towards a terrestrial existence changed, and they wound up stagnating, and they have now stayed amphibians that are attached to water, and they never truly colonized land. That's the quasi-terrestrial. And that was all done when the fossil fuels, those boggy conditions, compressed. And what coal is all that plant, boggy, animal life, a lot of marine life, that was literally compressed, and all of the water was squished out of the carbon gook. And 96% of the water was pushed out of this, which made the coal, thus the fossil fuels. When you hear about fossil fuels, that is what they're talking about. And when you hear about fossil fuels, it was the age of the amphibians being the dominant vertebrate life on land. Questions? One story. My favorite of all amphibians. Let me see if I can pull it up quick. Anybody have a guess who's been here before? It's a frog. My favorite of all amphibians is the wood frog. Anybody know why?
No.
The wood frog is the ultimate frog as far as making its way north. Wood frogs actually live above the Arctic Circle. And so we talked about the green frog and the bullfrog going down in the mud in order to survive the winter. This guy, often called the robber frog because of its mass. If you're above the Arctic Circle, can you ever get under ice in the winter? It's called permafrost. So this frog will literally not bury itself to survive winter. It will just go under the leaf litter, and it just can freeze. This frog, when it goes under the leaf litter, it was found by, I think, John Burroughs, other naturalists, just walking through New England in the winter, and they turned over a leaf and, scraped it with their foot, and they found a wood frog. And it was frozen. And, being a naturalist, brought it back to the cabin where he had a fire going, just kind of left it on his desk. And as it started to warm up, guess what happened?
It melted and it lived?
It lived. And it started really investigating wood frogs. And of course, most of the research was done above the Arctic Circle. It turns out that through the growing season, they store tons of sugar in their liver, tons of glycogen. And just as it starts to freeze, usually at one of its toes, it will pump all that out into the fluids of the cells, like antifreeze. But at the same time as that fluid's coming in, little protein particles are pumped out of the cells. And if we take this glass of water, we could actually cool it below freezing, as long as there's no dust, no movement, no contamination. But once it gets below freezing, if I throw a little particle in, guess what will happen? It will instantly freeze. So you can, literally the glass would explode. If we brought that below freezing, threw a snowflake in it, well, that's what the wood frogs do with the little particles of protein. Once they get to that freezing temperature, it causes the interstitial, the fluid around the cells to freeze. acting as an insulator for the cells that are packed with the sugar and the antifreeze, and they remain frozen without the cell damage all winter long. Technically, they kind of changed the human perspective of what life and death is, because they have no heart rate, they don't breathe, they have no metabolism, they're just in this frozen state. And then come spring, or inside a cabin, when it slowly warms up, they come back to life. Did you ever hear of Walt Disney? Cryogenics, freezing himself for the future? That's where it all came from. It all came from the wood frog. Isn't that amazing? Changed the definition of what we believed is life and death. Have you ever heard of stories where someone drives off a bridge, they go into the icy water, and they're without oxygen for 20 minutes, but yet they're able to be brought back and revived without brain damage? Yeah, so the wood frogs are kind of a pioneering animal that's been used in medicine to really discover, like, what can we do for stroke victims? What can we do for human diseases? I don't like to think of animals just being used for just human concerns, but in this particular case, this species has been used in a lot of ways to learn about how to help people. But my reason for really loving the wood frog is just the uniqueness and just the unbelievable resiliency of this amphibian to really conquer all of North America and live just about everywhere. Good? All right. So, now that we've learned all about amphibians inside, don your water shoes. We need water, we need your snack. Bring your lunch, because we'll probably eat the lunch outside too. Bring your second snack, because who knows how long we'll be exploring in the streams and looking for these amphibians. Let's get our gear and let's get going.